Sure. Okay. So I want to talk a bit today about active inference from the perspective of perhaps some emerging industrial opportunities that I perceive, because as I was just explaining before we started, I'm not a researcher or in academia. I've spent all my career in industry, but I do think a window of opportunity is now opening for some of these areas I'm going to talk about, and it really is just two I'm going to talk about. And I think the opportunity for active inference now is certainly increasing, and really these two use cases are just two examples of that. Um, so my background specifically is, yeah, I had about 28 years career in the semiconductor industry, mostly startups, but also some big companies. And I'm currently at Synopsys, which is a big EDA and silicon IP company. Um, and I'm a distinguished architect at Synopsys. And then previously, I've been sort of architect fellow type roles at places like Graphcore, which did the world's first commercial cloud XPU from about 2018 onwards. Um, and also at Imagination Technologies doing embedded GPU technology and various roles in various types of chip design prior to that. And really my interest today is sort of mainstream high power AI infrastructure in the cloud, which is a lot of what my sort of work at Synopsys pertains to, but also things like neurosymbolic computing, neuromorphic computing, continual learning, some of these emerging computational paradigms that are related to that. Things like p-bits I'm talking about today, but also things like hyperdimensional computing, novel memories, model computing, et cetera, et cetera. And then sort of mainstream use cases, electronic design automation, thermal management devices, telemetry, stacking of chips, a whole bunch of stuff. Um, so that's my background. And before I go any further, I just want to put in a quick disclaimer that although I work for Synopsys and I'm here today with their permission and blessing, essentially the interests I'm talking about are basically, at least today, my own interests rather than Synopsys. So I don't have like a big sort of research agenda on Synopsys' behalf behind me, nor a big bucket of funding for anything. Who knows? Maybe one day that could change, but that's not the case today. So I just wanted to set expectations on that front. So the two use cases I want to talk about today are these two, both with respect to active inference. And maybe just to be clear for everybody, I actually explain what active inference is. It's basically a formalism that Carl Friston and his collaborators came up with, which is related to intelligent systems which can perform inference by acting upon the world and then having their own generative model of the world that predicts what state change in the world their action will result in. And then when they get the feedback from the world sometime later, they can determine what, through their generative model, whether that feedback is surprising or not surprising, and they aim to minimize their surprise, which is formulated as energy minimization of that active inference. So it's very much a physical AI type thing because it's all about acting on the world. And when you act on the world and you have a generative model, it's not end-to-end differentiable. So you need new paradigms to deal with that. So this concept of active inference, act on the world, receive feedback, model the world, minimize your energy. So to aim to minimize your surprise and maximize the efficacy of your predictions can be applied to these two problems. The first of which is orchestration of large heterogeneous computing clusters, which are now they're talking 125, 300 kilowatts per rack, going up to a megawatt per rack one day maybe. And these are heterogeneous computing scenarios where you've got many, many jobs running all at the same time. Jobs have timescales of years to milliseconds. And when I say years, I'm just talking about, workloads can evolve over that time. Even though the infrastructure might be fixed, the workloads do change over time scales, obviously from milliseconds, but they do evolve on slower time scales as well. And it's a nice full stack problem because you can intervene in these cluster orchestration problems anywhere from individual devices, of which there may be thousands of millions in a cluster, all the way through up to schedulers and really the management of the entire cluster, which includes things like its sort of lifetime management and reliability management, all that kind of thing. And the question here that I want to sort of motivate this with is Could we potentially get a 2x reduction in the total cost of ownership of that infrastructure through smarter active management? So that's use case one. And use case two is this concept of P computers and P bits, where a P bit is basically a nanoscale source of entropy, not necessarily completely random, but controllable. So you can sort of control the oscillation between 0 and 1, and then aggregate all of those separate sources, mini sources of entropy. So you can do some really cool stuff, like, for example, sample from arbitrary probabilities distributions, which then enables on top of that, more tractable approaches to Bayesian inference or active inference, either in the cloud or at the edge. And a lot of the sort of p-bit summaries give this sort of like progression. You've got your logical bits, which are always 1 or 0. You've got p-bits, which oscillate between 1 and 0. And you've got these q-bits where you're talking about superpositions of those states. So I'll suggest how active inference could fit there. So in terms of cluster orchestration, there are many sort of HPC use cases out there. There's just two examples I have here. The first is generative AI inference at scale, which is basically these days means token level scheduling. So you've got like hundreds of users you're serving on a given rack of equipment, and you orchestrate that token by token. So you don't like orchestrate this request from that user and this request from that user. What you do is you basically slice all those requests on a per token basis. So each token you generate for multiple users, which have all got queries of different sizes, you do token by token. So it's a very fine-grained these days orchestration problem. And they've had to do that in order to get the sort of load balancing and the latency and throughput trade-offs as optimal as they can be, given the methods they currently use, because these requests are also heterogeneous in terms of their sort of like the size of the context window, the amount of output they have to generate, and so on. And then another example from my sort of synopsis world is this idea of EDA and physics simulations, where you've got a cluster of compute, many just CPUs, and then you've got thousands of jobs to run, tens of thousands of small little jobs that do a little Verilog simulation or a little bit of synthesis or something, through to like massive jobs that use terabytes of memory, lots and lots of compute, lots of cores. And all of those jobs tend to, even within one job, quite heterogeneous in the sense that the memory pressure, the compute pressure is going up and down throughout their job. So you can imagine when you mix all of these together, quite difficult to utilize all the resources effectively. And you've got a lot of stranded and wasted memory, all of which becomes very visible to the people who are using that infrastructure. So can you do better than that? And then there are these other issues around like jobs that have got KPIs and service level agreements. You've got to get your tokens through at a given latency, because that's what you've promised your customers as a sort of AI factory. And on the EDA side, time to results matter, but also some jobs have higher priorities than others, or have a max memory limit and so on. So you've got to try and hit those KPIs and SLAs and maximize the sort of utilization of the compute resources, and then sort of deal with some of these other issues, like the fact in the AI clusters, your GPUs are burning out after 2 years. You've got to keep tabs on the health of each device, as well as deploying work onto them. And then you've got the networking that glues these clusters together, which fails and has all kinds of issues, like dynamic issues like congestion and all that sort of thing. And then this whole thing is becoming more and more power dense, where NVIDIA racks today 125 kilowatts each, just one rack, and they're talking about getting to a megawatt by sometime after 2030. So it's extraordinary power densities, with liquid cooling and everything, which really make the problem quite difficult. So the way I would frame this for sort of an active inference perspective, if you look at the diagram on the left, I've got sort of my cluster from the individual chips through to the racks, clusters of racks. Then you've got a job that's orchestrating over many racks, and you've got some kind of scheduler there, basically, which is receiving job submissions, queues of work coming in to the data center in real time. And then you've got some level of sort of compilation or structuring of that work, compiling kernels, that sort of thing, organizing different schedules for doing the same piece of work in. So if you imagine that schedule level as some kind of active inference agent, it can receive telemetry from all those levels of the hierarchy, and it must emit orchestration uh, actions into that whole infrastructure in order to deploy work on it, um, keep tabs on failures and all that sort of thing, or things that may be about to fail while meeting the SLAs from the job submission. So the way I've always seen this is, active inference, you define an environment that the agent acts on. And here the environment is the combination of the infrastructure itself, so the hardware and its sort of layers of middleware software, which I can observe through telemetry and act on through the APIs I'm given to control it. Then there's also the workload environment, which I'd kind of see a bit more like, I don't know, like the weather, right? So we can predict the weather, we can't influence it very much. So while you can't really influence what work the world will throw at you, you can predict it. You can also look at job submission queues, so you can see what's in the queue, and you can potentially act on it to some extent, especially in terms of sort of restructuring jobs through recompilation or reordering or that kind of thing, um, to make them more amenable to whatever the current state of the system is. So I don't have any more detail on that to sort of put forward on this cluster orchestration problem, but I guess that the pitch I wanted to make is, and maybe this is a pitch, like you say, Will, perhaps more for the sort of ML group, but I do think that while job scheduling clusters is less sexy than cool robotics or autonomy or whatever, it is quite a rich multi-time scale environment, hierarchical environment, and it's these are high value infrastructure. It is complicated, and these are high value settings. So there's a lot of money at stake, and even small improvements make such a big deal. And because their power densities are so high, um, if you only took 1% of that power budget, that is actually quite a fulsome power budget to do some cool stuff with. And if you can use that to save 10 to 25% of the energy or TCO or runtime or whatever, that is still quite a compelling story. And I guess, from a sort of research perspective, these test beds, which are just, clusters running, complex heterogeneous workloads, whether AI or EDA or multiphysics or HPC, they exist everywhere. And they've got a lot of this telemetry and tooling and stuff built in. So although the infrastructure is not experimental, there's a lot of room for clever optimization approaches here. So that was the first one. And I guess that's kind of like a near-term use case that I perceive. Slightly further out, we have P computers. So what it is, a P computer is composed of P bits. And the P bits, like I said earlier, were basically, if we consider a Boolean or logical bit as reliably 0 or 1, and Q bits are a superposition of 0 and 1, a P bit will oscillate between those two states, but with a controllable probability. And while logical bits are small, we know qubits tend to be really big. P bits would ideally be small, like logical bits. Not maybe as small, but small. So you can fit millions or billions of them on a chip. And if you can do that, then you can enable computational manipulation of probabilities at sort of chip or multi-chip scale, which you can't do with, linear feedback shift registers and other pseudo-random or software-driven sort of probabilistic manipulation, because the cost of those sources of entropy and transforming them from their sort of baseline uniform or Gaussian distribution, whatever distribution you want to work with, is so incredibly expensive. So the dream of P computing and P bits is you've got hardware that will allow you to sample from an arbitrary probability distribution, which could be quite complicated by modal, um, that sort of thing, and do that with sort of petabits of random bits per second on a chip in these arbitrary probability distributions. And that's basically what a P computer is. And this whole field, as I go through these slides, I've got some diagrams, and I've cited where I got them from, and they basically come from just two papers, both of which give you a really good summary and overview of the p-bits sort of literature that's out there, and the state of the art. So if you wanted to get a good sort of academic summary of the space, these two papers are what I would suggest. So the way they work is this sort of at a most fundamental level, you have this concept of a coin flip primitive. So a coin flip gives you a 0, 1, heads or tails. but with the added feature that in principle we can control the probability of that 0, 1 on a sort of per flip basis. So from that, with that primitive, you can basically build an arbitrary probability mass function by flipping the coin many times. And you imagine you go to each uh, density bin of your PMF, and you start the biggest density bin, flip the coin, and if you get ahead, you stop. And if you don't, you go to the next highest density bin, you flip again, you stop when you get ahead. So you can see how that allows you to build up like sort of arbitrary probability distributions where you define your density and then you flip your coins. And there are various ways, which I won't go into now, for handling things like continuous probability distributions and multi-bit probability mass functions can all be constructed by sort of aggregating these p bits in various ways. So that's the basic sort of modus operandi of a p-computer. And the way you build these devices, and there's many suggestions in the literature for how you build these sort of controllable sources of really low-level nanoscale entropy, but there are basically two methods, and the first of which is shown here. So method one, you have a two-level system, and you've got an energy barrier, which is shallow. And then if you've got some thermal noise, you will end up transitioning between those two um, shallow troughs. And the way you tune the device then is you make one trough slightly bigger than the other. And that way it'll obviously spend more time in that trough than the other. And then the second method is you have well-defined states with a tall barrier. So if you look at like dot two, you basically arrange to bring that system to the unstable point where the ball's at the top of the tall barrier, and then thermal fluctuation will push it one way or another. And you tune that by just positioning your device slightly to the left or right of that unstable tall barrier. So I'm not going to go into all the device physics and options behind all of these, because that isn't really the point of today's talk. But you'll, again, in those two papers, you'll find lots of examples. I mean, there is one example. This is sort of the canonical p-bit, which is a MTJ, a magnetic tunnel junction, sort of modified from its original use in MRAM memory. And one of the key things you need for a successful p-bit is you need some kind of thermal noise that you can leverage without needing an amplifier that's much bigger than the device itself. And you need to be able to control that device again without adding much area overhead. Because as soon as you 10x the size of the device, you've kind of lost the nanoscale point of P computing. But because they're so small, even if you achieve that, they are going to be severely affected by manufacturing variation and environmental variation. And you'll also find that some of these p-bits may have endurance issues. So really the problem for the sort of p-bits community is not, can we make p-bits? We can make p-bits. How do you actually control them over the duration of an application run? And that's where I think active inference is going to come in. But before I get to that, there are a few different architectures you could employ. So in architecture A, what we do is to implement, for example, a component of a Bayesian neural network I'd like to store in my memory, my classical memory, a mean and a variance. And then I'm going to read them out, and then I'm going to put the variance to control a p-bit, which is going to flip my coins, and then I'm going to end up with a distribution based on that mean and variance that I read out my memory. The second thing I can do is I could have, so in case B here, I could have actually the p-bit sort of integrated with that memory cell, and I can read it multiple times. And if it's got a given probability distribution, I can build up a distribution that way. Or I might have many p-bits, each with a less perhaps individually controllable stochasticity or probability of flipping a heads. And then if I can combine those somehow dynamically into a group which, given their individual behaviors, approximates the probability distribution I'm interested in, I can do that. And that's the sort of population-based approach. So that lots of different ways of sort of building these things up from their classical primitives, which will depend on like what application you're trying to do. You're trying to do a sort of Ising spin glass thing or a sort of Bayesian neural network type thing, and what is the nature of your physical primitives. And there's a bunch of people building these or have built them. Quite a few have been built by university programs. And then, like I said in the opening before we actually started the recording, there are startups such as Normal Computing who are building stuff with p-bits, albeit more on the sort of thermodynamic computing side of things. So lots of activity in this space. So this is my pitch now for active inference. I think it would be really interesting to see whether active inference is a paradigm, an approach which we could apply in order to render the millions of p-bits on a p-computer usable by dynamically mitigating the device and environmental variability. So what would it do? It would basically predict the unwanted drift in the reliability or the controllable probability of these bits. It would act on the state of that P computer to target some desired level of the entropy quality, either at the p-bits level or at some higher population level, depending on what your sort of p-bits architecture is. So, for example, if you're doing the population approach, you might be, importing and exporting p-bits from groups. So you over time you're keeping some group of p-bits approximating some kind of probability distribution. And of course, that probability distribution could change because you've deliberately changed it because you've updated your prior from your posterior or something like that, or because the device is misbehaving. Or if you treat them individually, you could, for example, have a bunch of p-bits that you're working on fixing and trying to tweak their various physical parameters that control probability or which groups they might belong to. Excuse me. And you could predict which, p-bits might be needing attention next. And in principle, you could learn the behaviors of each p-bit, depending on how many there are. Maybe if you can group them according to sort of common behaviors or location or whatever, and you've got some other memory resources there to do that. So that's kind of the what you would need to do. Then I think the other interesting part of this, and again, why I think it's sort of interesting with this group is this notion of mortal computation. So one of the things that originally inspired me around all this was reading this paper by Carl and Alexander on this mortal computation principle. I don't think they coined the term. I think that was Geoffrey Hinton that did that. But I love this paper, and it kind of explains how you might build sort of a mortal computer, how you might deploy active inference, and all the sort of concerns you have when you build such a thing. And I think this is a mortal computing problem, this P computer problem, because we're essentially saying that the P computer running active inference could use its own P bits to implement the operating system that manages that wider P computer, for which most of the P bits will be made available for some other useful computation. But you've got this little sort of operating system that's keeping the device in a state where it's useful for whatever that workload is. So it's keeping itself alive using its own substrate, using its p bits, because one would imagine that an active inference process is going to be able to leverage those p bits to do a good job. But it's got to modify its own substrate to do that, so that whatever the workload happens to be makes forward progress with, and the state of the P computer is kept stable at least long enough for that workload to complete. So kind of like quantum error correction in a way, but hopefully much, much easier than that. So then you could ask, okay, let's imagine we've solved that problem, or let's say the active inference community or whoever solves that problem. What do you do with it? I think the answer is what you do with it is more active inference. So there are lots of obviously use cases for a workable P computer. It allows you to do principal Bayesian methods, active inference in a single chip. It could enable a whole new load of machine intelligence use cases which are able to handle out of distribution and confidence scoring, whether at the cloud or the edge. I also think that that if millions or billions of p-bits could be tamed really by an approach like this, I think whoever achieved that would be the people technically and philosophically equipped to dive into a whole bunch of other mortal computing possibilities, whether it's using p-bits or not, because a lot of the insights will of course translate. And I think also here, if this can be done, or even if it can be partly demonstrated, then it competes with quantum quite effectively. And I always think that if these kind of things got even 10% of the capital that goes into quantum, where we might already be. So I've just got a couple more slides now, and then I'm done. In terms of practical research approaches here, for cluster orchestration, like I said, it's fairly straightforward. There's lots of stuff out there. The performance gains you get are really easy to quantify. And I think there's a lot of potential compelling reasons for commercial entities to want to fund research in this kind of area. But it is a complicated, rich dynamic environment, which is hierarchical. So it can admit the whole sort of paraphernalia of mortal computing with Markov blankets and all that kind of stuff. And I also think it's a great way to prove active inference in the real world in a way that's perhaps, I imagine, might be easier than working with a robot or something where you've got a load of complex actuators, hands, or whatever. Although this is a sort of solid state environment, it's still a very complicated environment, but perhaps easier to work with in some cases than truly embodied physical AI. It's still hard. I'm going to call it the easy win there, only because I think it's easier than P computers. But I think there's still a deep vein there. And then on the P computer side, I think, although they don't really exist today, I think p-bits and active inference, sort of the inner loop of that, would be extremely amenable to simulation. And I also think you could do it quite a lot for just emulating these p-bits on FPGAs, which would allow you to do more. And I think although there's an awful lot of work on p-bits around the sort of physical devices and also some on the workload, there is just not enough on how do I actually make this thing work? The practicalities of building that P computer operating system, I think, is lagging. And a lot of the workload actually research around p-bits applies, p-bits sort of coupled into big sort of Ising spin glass type networks, and you iterate those to try and solve optimization problems. But I think, it would be nice to see more workload research there in terms of actually leveraging the p-bits in terms of these sort of controllable probability distributions for Bayesian networks, active inference, that kind of thing. So there's plenty of scope in this field for sure. So my last slide, the research questions I'd ask here is, is active inference a good fit for heterogeneous computing cluster orchestration? If you had 1 to 5% of the cluster's compute power budget, what could you do with that? How much could you save? And then the rest of them on p-bits, can an active inference operating system successfully operate these machines so as you mitigate all the variability issues? And if you can do that, could that active inference process that manages that P computer actually run on the same substrate it's managing? If you solve that and you had a device with a bunch of p-bits, how many p-bits and what type of architectures along the lines of the ones I've described would be the best fit for active inference to actually then take that into other sort of workloads where you're actually applying that to real world problems? And then related to that, if you had these p-bits, would you do the sort of spin glass optimization type approach, which could be very good fit for energy minimization, or would you take like more of a BNN type Bayesian approach? And then finally, the commercial question: if we could demonstrate, as a community, the efficacy of active inference for something like cluster orchestration, I mean, there might be other alternatives. Does that provide any useful evidence that actually says that yes, we could solve the p-bits problem? And if you could, then I think that would really help to make the p-bits, the whole p-bits thing, more investable from a sort of venture funding perspective. So that is all I had. How am I doing for time, Will? Roughly on time?
Yeah, absolutely spot on. That's brilliant.
Okay, good. So over to questions, over to Carl.
Great. Thank you so much, Dan. That was Fascinating. Such a cool concept of active inference, leveraging the p bits, and then also
I mean,
using.
none of it's my idea, right? I'm not.
Yeah.
I'm just here, sort of raising awareness of it, really.
Mm. Okay. Does anyone have any questions? If no one has one at the moment, perhaps could you give a bit more detail on the sort of problems this operating system would be solving with the p bits? You mentioned drift and change in behavior.
Yeah.
Yeah, what's the sort of scope and nature of those changes?
So there'll be things like an obvious one is, so when you make all these, like, if you imagine the where is it, the MTJ there, right? So this is just a transistor, right? And it's constructed and biased so you get this oscillating behavior between 0 and 1, and you can control the probability of that by controlling the voltage that goes to it from a sort of sideband control. Now, obviously, those are nanoscale devices, so individually across the chip, they're going to have slightly different parameters, right? So each one will need to be controlled. If you want to get the same probability, for example, between 0 and 1 over all of those devices, and you may have millions, you might have to bias each one slightly differently. So how do you work
Right.
out what is the right point to put that bias at? And then you've got things like temperature drift. You can imagine that the oscillation is certainly, I mean, we're talking about thermal noise here, so the temperature really matters. So ideally, you would keep the temperature of the device within some range. And if you can't, and you may not always be able to, then again, you're going to need to manipulate the device's sideband controls in order to deal with that. And dealing with that is much easier if you can predict what the temperature will be at the next time step.
Mm.
Then now you can take preventative measures, should be what active inference is all about. Predict the state of these devices at the next point in time using whatever model I have of them, enact the controls to try and keep them all operating at the right point. Whatever your objective function is that you derive for that, and then measure your error when you actually then get the feedback from how those devices are behaving. So temperature drift is one, but there's also things like the the power supply to the chip is obviously the energy is being consumed by all these devices. Power supply is noisy potentially, introducing additional sources of variation. You've typically got process voltage and temperature, where process is like the manufacturing process differences I talked about. So one p-bits device and another p-bits device, although they're physically the same, they've got different manufacturing variations. So your set point for your operating system on this one is different to this one because they've got different range of manufacturing variation on each device. For example, if you have a wafer of these chips and then you slice them up into individual chips, the ones near the edges of the wafer will typically have a manufacturing variability profile different from the ones that came from the middle of the wafer. And you can potentially learn, right, which part of that space your given device is in. So that's process, and you've got voltage, like I said, the voltages are never perfect, so that's gonna bias things. And then you've got the temperature side of things, which is particularly difficult. I mean, you can potentially keep these devices. I mean, imagine you put all these p-bits devices in an immersion cooling tank. So rather than keeping them cool, what you're trying to do is keep them at a constant temperature, and that might be easier in an immersion tank than in air or like with cold plate type cooling. So there are various things you could do to make the environment more benign, but you've still got a lot of hard work to do, I think, to realize the dream of p computing at nanoscale.
Mm. Okay, thank
Answer
you.
the question.
Yeah, yeah, definitely. And then what are the what would you say the more standard or existing go-to control and optimization processes companies might normally jump to for these kinds of problems, also for the cluster orchestration?
So for cluster orchestration, what the people do today is they look at the telemetry from the devices. So you might have, in your CPUs, you've got counters that give you cache misses. You've got counters looking at the memory bandwidth or the memory memory bandwidth utilization you're getting. You've got things like how much memory is used on a given machine. You've got the temperatures of all the devices. You've got networking telemetry like congestion and switches and all that sort of thing. And what they do is they suck all this telemetry out, and they normally use that for health monitoring or for monitoring efficiency rather than reacting in real time. Because a lot of these clusters, if you take a big AI cluster, it runs synchronously. The GPUs all do the same thing at the same time, and then they get to a barrier, and then you wait for the last GPU to catch up, and then they all continue. So when you operate them synchronously like that, there is a limit to how much clever optimization you can do without breaking that synchronous operation. I
Mm.
think there is more interest now in operating them asynchronously, whether for training or inference, and that admits, a richer variety of possible controls. But even if you're synchronous, um, there's still potentially a lot you can do to decide, well, okay, I've got 100 inference jobs I need to somehow put on this cluster all at once. If I know how long each job is, I can potentially try, or how heavy in terms of compute capacity, memory bandwidth, whatever it is, I can spread them about more effectively. And I can also be doing things at the same time, like checking which of my devices are starting to become marginal, starting to burn out, or suffering from a higher degree of memory errors than other devices, and I could avoid them. Or I could somehow put work on them which is more separated, so I don't have like a laggard slow GPU in a group of good GPUs. It'd be better to have
Mm.
a group of bad GPUs that sort of you give the low priority stuff to, or something like that. But a lot of the cluster orchestration these days tends to be about health monitoring and sort of fairly coarse grain. Is this machine free or is it not free? And where have I got the KV cache for this user? Um, the industry hasn't really exploited, I don't think, all the degrees of freedom you potentially have in a system like that, because that's very complicated, because that needs more sophisticated methods to manage it, and because if you do that, you may get more variable performance. You might overall optimize the TCO, but this job could take longer. So many more degrees of freedom to be exploited there, but the industry is quite cautious in like trying to exploit those because of those issues.
Right. And yeah, maybe one more question before pass over to Carl. Yeah, you mentioned that the p bits could be emulated.
Yeah.
Um, yeah. So what's the sort of procedure there? How realistic can we get? Because I imagine that trying to learn the right generative model is going to need a lot of experimentation and really probing
Well,
the
to some
behaviors.
to some extent, if what you're trying to do is answer the question as, given you could imagine a p-bit, that some approximation of one of the sort of styles of p-bits that are out there in the
Mm,
literature. I don't think that we need it to be, if the question you want to ask is, can I sort of devise an active inference process that can handle these kind of phenomena? I'm not sure you need a very faithful representation of that p-bit. What you kind of want is a population for which you've got some of these variation effects, the static manufacturing variation effects versus the dynamic ones, the temperature, the voltages, all that sort of thing. Um,
mm,
as long as they vary in plausible ways over
right.
sensible timescales, and they implement an API for controlling them, which is sort of reasonably faithful to the sort of typical PBS you get there. You don't then need, I don't think, any more than that in order to develop active inference approaches. But then if you want to take a particular p-bit, a particular physical implementation, that's where you can run physics simulations of those devices, which those research groups will be doing. They will have a physics model of their p-bit, and they will run simulations to see how they behave as they vary the temperature, and they vary the manufacturing parameters like the channel widths and all that kind of thing. So if you took that physical simulation of a small number of p-bits, and you had already developed like an outer loop or an overall algorithm you wanted to use to apply this, I could then perhaps take some portions of that inner loop and do all that in simulations. So we're talking about a physics simulation, essentially, of the p-bits, feeding into whatever sort of control algorithm is built that's gonna control those and build a model of them, a generative model of them. Or on FPGAs, that kind of goes back to what I was saying about build an approximate model of a p-bit, right? That is cheap to model, but in aggregate gives me the sort of behaviors I need to test my higher level approach and algorithms. I could put a lot of those on an FPGA perhaps, and it might not be that the stochasticity won't be fully independent or really that high quality. So you wouldn't run a real workload on a P computer done like that because you need them to be you need certain guarantees about your entropy and all that sort of thing in any of these use cases. But for sort of building algorithms that can predict how these things behave and then apply all the paradigms of that active inference to then actually sort of build a loop that keeps this thing stable, I think could then be done at a higher scale on the FPGAs. So there's a few different approaches in there, right? And it depends whether you're focused on a particular device type implementation like the MTJ, or whether what you're really trying to do is work at a higher level and build sort of, the sort of overall paradigm or recipe for solving this problem.
Right. Thank you.
Can
Bruno,
I,
do you have a question?
yeah, jump in there? And thank you, Dan. I find this always very interesting, and thank you for putting this together. A couple of points here is that within training clusters, I mean, I learned this from friends at OpenAI. They started moving away from complete synchronization many years ago, because what they found is that they would blow out their power on the power demanding stages, particularly the high compute,
Mm.
high compute phases. And so what they would do is that they would deliberately slow down the cluster to keep it within the power threshold that they had to avoid, tripping breakers.
Mm.
Um, one of the I think that they're doing more sophisticated things now, I think, towards this direction, but I agree that there's lots of many dimensions that they haven't all, optimized yet. Um, what I wanted to understand is trying to think through about, I can understand the value of p bits in a proof point for improving the manufacturing process, and dealing with drift, manufacturing variation. There's also, but I was trying to think specifically about what is the commercial driver and unique product value in that PBATs, I presume, would be stronger when it came to, entropy used for cryptographic,
Well, I think it's about, if you look at a Bayesian neural network, what it's doing is it's confidence scoring, right? It's able to rather than each weight being like a fixed point weight like you get in neural networks today,
yeah,
each weight is a probability distribution. So you forward pass, you're taking a sample from those probability distribution. You do that a few times, and then you get a confidence score, which is what you don't get with an LLM. And the whole principle of Bayesian inference, which is
hmm
a concept that long predates LLMs and the current generation of AI, is all about you have your prior beliefs. You observe some data from the world, and when you combine that with your prior beliefs, you get your posterior belief, which is a principled combination of those two pieces. And once you've got your posterior, you can update your beliefs. And the degree
yeah,
you update your beliefs is dependent on how sharp that your prior beliefs were versus how sharp your posterior ends up being when you've seen the evidence. But that level of control of probability is completely beyond today's computers. You can't do tractable Bayesian inference, probably even in the brain, in its full sort of analytical form, and you can only approximate it even biology. So so if we want to have AIs which are able to cope much better with out of distribution data, you need techniques like this to deal with that because that's what the brain does, right? The brain has got these sources of stochasticity inside of it. Somehow it manages to do this and leverage the intrinsic noise that's in there and put that to use somehow. And Carl will have more ideas on this so that noise doesn't go to waste, and you use it for these reasons. So the way this kind of stuff is done, like also in physics simulations where you're doing Markov chain
Mm.
multiply, where you are sampling from arbitrary probability distribution, is incredibly expensive. So you would speed all of that stuff up. And then the other answer I would give is stuff that a quantum computer would do, or people often suggest here's a workload for a quantum computer, often will also be fit well on a P computer. Um, and the difference is, okay, it's not got the full power of a quantum computer, but once you've got a P bits chip, you can scale that. Whereas scaling a quantum computer is really, really difficult. So for some workloads, the answer might be P computing is a nearer term alternative to quantum computing, which in many cases might be just as good and more scalable. So those are the two answers I'd give.
But you're very concrete about this, Dan, and it's maybe something I don't understand enough about Bayesian inference. Is that I contrast this, for example, a graph core, they had a pseudo-random number generator hardware specifically built
Yeah,
into it.
yeah.
And and for many applications, the entropy you get from that is, you know, of practical equivalence to what you would get from thermal noise. And understanding what is the sort of like the unique value that you get of p bits compared to the entropy from,
You just get much more of it,
yeah,
right? So there are
yeah,
plenty of chips today with a very small quantity of fairly high quality, entropy
yeah.
generation, right? But nowhere near enough to do the kind of things I was just talking about. That's the difference because you're talking about a circuit that does that today on most chips. It'd be 4 or 5 orders of magnitude bigger than a p bit, or even more.
Mm.
So you just cannot get enough of them, and obviously you can't use one little bit stream of entropy to do your entire physics simulation or your entire Bayesian inference. They all need to be independent, and you need them all running in parallel, which means they need to be really small, right? Which also makes them
So
very energy efficient. Because if you're using a big, LFSR plus some software then to, craft some probability distribution from that, that is very computationally expensive.
so the idea is that it's a massive reduction in the PPA for that entropy generation then.
Correct.
Yeah.
Correct. Exactly.
Yeah.
And once you've got that, you can do a load of amazing things with it that are completely intractable today otherwise.
Got it. I was just going to put a link on. Carl was just speaking on the Ion AI podcast. So I just put a link in the chat. And then should we give over some of the time for Kyle and anything he might want to ask about?
Thanks, Bruno.
Yeah.
Cool. Thank you. Yeah, over to you, Carl. It's your turn.
It's my turn now.
Yes. Oh,
Okay,
yes.
very good. Yeah, fascinating and great conversation. Um, so a number of things came to mind, but I should qualify that by um, saying that this is completely outside my comfort zone. This is high-end computer science and the sort of things that um, I hope to see crafted in my old age and retirement. So all I can really do is sort of say, yes, that is absolutely spot on. And from a neuroscience perspective, this is exactly what you'd hope to see develop in computer science and machine learning and artificial intelligence research without any particular practical guardrails or guidelines as to how you might do it. But certainly everything you've said makes entire sense and would be, at least in terms of a sort of narrative white paper, very easily motivated from the perspective, as you've noted, of mortal computation from the point of view of natural intelligence, and also I think from the point of view of the physics of computation, which in one sense could be read as the thermodynamic computation. But I think more broadly the intimate relationship between um, energy and information. So I'm just going to give you a stream of consciousness, really just to say, yes, absolutely. And if you can find a bright young thing to make these ideas work over the next decade or half decade, then I truly hope that it can be done. Um, I think from my point of view, there's sort of two key themes here. Um, one, and one I think slightly folded into the other. The first key theme we've already mentioned, which is model computation. I think what you're talking about now is if you want to make computers um, efficient in a way that is sustainable and do the kind of things that you hope computers will do in the future, then they have to comply with the right principles of least action. Um, and as such, the information processing will hopefully approach Landauer's lower bound. Um, and that immediately calls into question the utility of von Neumann architectures, and immediately you start having conversation about processing in memory or in memory processing that I imagine is the same kind of conversations you might have with people doing memristor research and possibly even sort of p-bit research. Um, but I think there's an important point to be made that you can't do any of this if you're still contending with the Van Neumann bottleneck or the memory wall. That's 99.9 recurring percent of your energetics just reading and writing to memory. So um, in that spirit, I imagine that the utility of the p-bit is being able to do everything in processing in memory in
Yeah.
in exactly the sort of way that you'd be directed to from a sort of mortal computation perspective. So I thought that was an important point to make. The the other thing that occurred to me was in terms of the first application, cluster orchestration and all the things that you were talking about that is entailed by orchestrating in the right way. Um, it did remind me enormously
Do you want
of
to listen, Bo?
yeah.
Oh,
Hello.
sorry to interrupt you, Cal.
No problem. Um, it reminded me of attention. And I'm not talking about attention heads and transformers, and I'm not talking about attention slots. I'm talking about how the brain does this. And One useful perspective on attention in the context of theoretical neurobiology um, is in terms of this kind of orchestration, um, where you are effectively enabling action on the inside. And I think that's important. So sometimes referred to as covert action. So when I attend to this or attend to that, that is an action, but it's an action which you can't see from the outside. You don't know whether I'm attending to this part of the visual field or this frequency in my auditory input. But I have to carefully evaluate what I should attend to. Um, and if it is a mental action, it will now yield to the principles of active inference. So if you can cast the orchestration problem as a problem of internal action in terms of message passing and belief updating or belief propagation um, in the computer, then I think you're now in a very powerful position to just simply deploy the least action principles in active inference to do that in the right kind of way. And what comes out of that is something which is very, very close to a number of things that you reviewed for us. So in the predictive coding implementations of active inference, specifically message passing or belief propagation under continuous state space generative models, so that now your implicit generative model is cast in terms of continuous variables that can range from minus infinity to plus infinity, and probability distributions over these, most usually this sort of exponential family. And in particular, for predictive coding, it's a Gaussian distribution, which means that everything can be reduced to second order statistics. But the interesting thing here um, is that the free energy minimizing process, um, which is one way of describing predictive coding. It's one way, which is the same, formally identical to Bayesian filtering, which is formally identical in its simplest case to Kalman filtering, which would be in an active context, formally identical to linear quadratic control. The free energy is being an extensive quantity, is as the sum of precision-weighted prediction error throughout your hierarchy, throughout your stack, throughout your deep model. And I think it's useful just to remember that, because the precision is an inverse temperature, and that gives you a very a seamless link to talk of getting the temperature down, or having the right kind of homeostasis, so that to come back to your lovely example, immersing your bit computers in some medium which keeps it all roughly at the same temperature. To my mind, that is exactly the kind of mathematical homeostasis to which the whole free energy principle aspires. It's just trying to describe systems that restrict themselves to a pullback attractor. That includes things like the temperature or the inverse temperature, which is the precision. So one view of attention in this context, and it's a view which has been unpacked in several dimensions, is that real systems like the brain that do the cluster orchestration properly actually have the ability to for precision control. So what that means is that there are certain messages, certain orchestrating messages or coordination messages that tune the precision of a population of neurons encoding some prediction error. And in so doing, if you assign them greater precision, then basically they have greater effect on everything, their Markov blanket, everything that they are connected to or in reciprocal exchange. But this, of course, in a hierarchy is local, so you don't need back propagation.
You're using precision here in a different sense to the precision of a neural network weight, I think, Carl.
Yes, I'm using it in its technical sense as a negentropy or a negative variance in the context of a Gaussian distribution. Yeah, the precision matrix would be the inverse of a precision matrix would be a covariance matrix,
Right.
and the log determinant of covariance matrix would be the entropy. So I'm using in the context of continuous state space systems. You can talk about the precision simply as the inverse variance of some probability distribution. I say that carefully because we're going to be talking about discrete state space models soon when we come to p-bits. But when I talk about predictive coding formulations, you're immediately committing now to continuous representations where the precision is just the inverse variance or the negentropy of a Gaussian distribution, and that can be thought of as an inverse temperature. Uh, um, in the sense that if I have very, very precise, if I have, think about simulated annealing. Simulated annealing would actually relax the precision of your random fluctuations and enable you, to jump here and there and to have a more dispersed probability distribution. But being very sort of cool-headed would be having very, very precise representations. So the picture that emerges from this is that moment to moment, every node, I was going to say every node on your factor graph. So I'm going to assume that we can always write down a computer architecture's message passing on a factor graph. And for every graphical model, there is a factor graph. So, if we just start with, there is a generative model out there. This generative model is implicit in the dynamics of my computer, and my computer has an interface, inputs and outputs, or a Markov blanket, and my graphical model, my generative model can be written as a graphical model. It will be inevitably deep. It will have hierarchical form. For every graphical model, every PGM, probabilistic graphical model, there is a factor graph. The factor graph then scaffolds or gives you the message passing on the belief propagation schemes. That just is the computer science of distributed processing on any architecture, ignoring the reading and writing from memory. But if it's processing in memory, then it can always be written down as message passing on a factor graph. So what this notion of attention as precision or attention as inverse temperature tells you is that moment to moment, you are always optimizing the precision that is weighting your local encoding on any one node of a prediction error. And if you decrease the precision, it will have less influence on belief updating elsewhere. And that basically means that you're trying to keep your precision sort of equal to 1 everywhere. So when things hot up, literally via the Jasinski quality, literally when they're using too much energy and when they increase their temperature, then you know that this means that there is an abundance of prediction error, more than I predicted. And that means that the variance is bigger than I predicted, which means I overestimated the precision. So now I have to reduce the precision. And in so doing, quench that local node's message passing or representation. So you get this sort of homeostatic effect of deploying attention if you can evaluate the posterior, not of the content, but of the precision in and of itself. So now it's not now just the weights that have a probability distribution over them, but the precisions also have a probability distribution over them. And this is quite a big thing in computational neuroscience, because in artificial intelligence and machine learning, people just focus on posteriors over latent states. And then posteriors, if they're sufficiently fluent and move away from machine learning, then they focus on posteriors over the weights, the parameters of your generative model in this instance. But probably the most important thing is the posteriors of your precisions. That's the thing that does the contextualization. That's completely missing, as far as I can see, in most of computer science and machine learning. Possibly with the exception of attention heads and transformers, if you sort of look at them in a particular way, you can actually associate these with some estimator of some fixed Kalman gain or attention. I should say the Kalman gain is a ratio of precisions. It tells you how much attention to pay to some observable time series in relation to your prediction before the update. So the Kalman.
Is there a good I don't know, written summary or paper on this that you could recommend, Carl? That sort of talking about this, focusing on the precisions rather than the weights or the latent variables or whatever.
Yes, in my little world there is. I'm not sure. Yes, I've got a few papers here. I'll briefly just for the recording go through, and then you can go back and pick up what you think might be interesting. But yeah, it's a good question. And immediately the paper that came to mind is um, quite a long way back in the literature on data analysis and time series processing. That was developed for the analysis of medical time series, in particular brain imaging time series. And it comes in various guises. Generalized filtering would be one of them. Perhaps the most interesting description of these schemes that emphasizes this mean field partition into states, parameters, and precisions, basically inference, learning, and attention, is called DEM, and it's called Dynamic Expectation Maximization, deliberately to try and engage the EM community, expectation maximization community. It's not actually expectation maximization, it's just variational Bayes, but under a mean field partition between things that change very quickly, the states, the things that don't change over an appreciable period of time, which would be the weights or the parameters, but then the M step, so that the dynamics would be the inference, the E step would be the learning, and the M step would be the attention. And the M step talks about a variational step that updates your precisions. And that can be done in a number of different ways. But from, I think, the point of view of your proposal, I think that's the key to deploying active inference to get the right kind of orchestration that you're talking about.
Maybe you're applying that both to the orchestration problem and the p-bits problem.
Not at the moment. I'm just going for the orchestration.
The orchestration, right?
Yeah. I think the p-bits issue has certainly a neuromorphic sort of lends itself to a neuromorphic discussion. But at the moment, no, you could apply what I'm saying at the moment. You could apply this notion of attention, formal notion of attention, um, to both a variational message passing scheme and a p-bit scheme, a mortal emulation. But I'll talk about that in a second. I just want to sort of reinforce that notion that there's a missing factor from the mean field approximation for any generative model in most of computer science and machine learning, which is not missing in neuroscience, because it's attention that basically equips us with the context sensitivity. And just for your interest, when it comes to deploying um, this computational neuroscience in the service of understanding people, it's usually a failure of attention that describes psychopathy. So in the computational psychiatry literature, it's 99% a failure to do the orchestration. It's a failure to keep the temperature of your message passing right. Attention deficit disorder, autism. Uh,
People not listen to the right bits of their brains is what you're saying.
Absolutely.
Yeah.
Yeah.
Yeah. No,
Yeah.
I get it. I get it. Yeah.
Um, so within that, there are two. There are three ways you can get your precision right. Um, or there are three kinds of architectures and three levels of sophistication in terms of what you might be able to build into your cluster orchestration algorithm. The first one is relatively simple, and perhaps at this point I will grab the screen
Yeah,
and
sure.
just show you the papers should you want to read. I'm afraid they're not they're not friendly to a computer science entrepreneurial audience. They are written for neurobiologists trying to understand the computational fundamentals of belief updating the brain. But the ideas, I'm hoping you'll get the idea, and potentially implement it um, in some hardware. Um, so yeah, let's just share that chap if I can. Excellent. So there are basically three ways of um, getting the attention right. You can have a local circuit. So this would be like having an extra little node or um, part of a computer, part of your computer that's just accumulating the prediction errors or the all the evidence for the context in which all this information processing is going on, that will be effectively gathering evidence that it's got its estimate of precision right, and then locally broadcasting it back to the source of that evidence. So this would be, I repeat, a local reactive kind of attention. In the neurosciences, this is known as um, um, exogenous attention. It's driven by the stimulus. So if I suddenly get some really noisy stimuli, or some really noisy input, um, or the rate of input suddenly increases, um, then I am not going to be able to handle that. And I'm going to, if I'm in a predictive coding context, I'm going to have lots of prediction errors, or the amplitude, the sum of squared prediction errors effectively is going to be much bigger than I predicted. And I can now take the Bayes optimal estimate of the posterior beliefs about the precision, and then implement those by down weighting the 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 prediction errors. So I'm decreasing my precision weighted prediction errors when I think I've got my when I think my estimate is too high, and vice versa. So it's an automatic control mechanism just to realize that if this input is like really noisy, I can ignore it by attenuating its precision.
Yeah.
Whereas if this input is very, very precise, and I've overestimated the prediction errors, I've underestimated my precision, I can increase the precision. And what that does in terms of the message passing, it homogenizes it. So everything, once it's been precision weighted, now has a standard deviation of one or a variance of one. So your computer, your brain is literally running in this nice
I
homeostatic.
think that's quite important for hardware architectures because that allows you to equalize, your burden of distributing messages through different routers and across different bits of the chip or whatever. If you can't predict the amount of communication that's going to suddenly appear, and you can't control it, you can't really keep the system stable. I guess that's your point.
Absolutely, and that notion that you've got this sort of computer in some kind of heat bath or coolant. It's always going to have fluctuations in the precision and in the work done in terms of erasing bits via the Zariski equality. But your job is to sort of allocate to sort of quell hot bits and pick out those bits that need a bit more heat, so enabling them to do more thermodynamic work. So you've got stuff sort of fluctuating, but always within limits as you're trying to predict the precision and the rate of belief updating, which is effectively the Kalman gain would be a nice metaphor for this. A ratio of precisions would be the rate of belief updating. Interestingly, just to sort of give that a bit of flesh, if you're trying to sell this to an investor, this is precisely why brain imaging works. So after a decade or so of doing human brain mapping, you start to realize that the hot spots you see in brain imaging that are reporting the local delivery of blood flow to support metabolism or the thermodynamics for the belief updating, for the erasure and updating of information, is exactly what you're looking at in these brain scans. So when you ask them to attend to visual input as opposed to auditory input, then the visual cortex lights up. And vice versa. And this is, if you like, and then an expression of this sort of intimate link between belief updating, movement on a statistical manifold, and the thermodynamic work required to move on that manifold. And it's delicate coordination, orchestration in biotic intelligence, in things like the brain. So. So that kind of very sort of, it should be relatively simple. The maths is actually almost trivial, so this is a biological aspect. So here's your sort of precision controller, which in the brain may be the pulvina a bit in the brain. I'm just trying to find something to convince you of the maths. Yeah, the maths is fairly straightforward in terms of predictive message passing with predictive coding. The second kind, so forget about that. That should always be there. And now we move on to much more interesting kinds of attention. Say, for example, you have now learned that whenever I'm in this context, say, it's this time of day, and these markets have opened, or I walked into the kitchen, you've learned where to look. You've learned where to deploy your attention because it's now context sensitive in a systematic way. That now means you can learn to do this exogenous attention control, and that becomes endogenous attention. From the point of view of the generative model, what that means is you've now got some latent states in your generative model, your probabilistic graphical model, upon which you can condition the attentional control, which means that now you can learn to attend to the right things even before you put yourself in the room or you started sort of greasing these pathways or tuning. And that leads to this kind of attention, which is much more close to people's understanding of our beliefs about uncertainty. So as soon as you condition upon some latent state, you're now equipping that latent state with the representation of confidence or uncertainty. That has now, if you like, been recognized by some cues in the environment or by realizing it's this time of day or I've just been switched on. And that now means that you can now learn to attend. You can almost amortize it, as it were. And this paper is all about this sort of second order or conditional deployment of attention. Again, the maths is fairly trivial. You can just now write down the precision as a lawful function of the states, and then you just invert the generative model. But now we've introduced a sort of second order kind of prediction into the generative model. Not only are we predicting the content of the next token, we're now also predicting the confidence that should be ascribed in this context. So now we have, oh, I'm in this tricky situation. I don't know what I'm talking about here. I'm going to have now, I'm going to sort of redeploy my attention to pick out the most informative sources of information, given I know I'm in this particular context. And this has been well studied for decades in psychophysics and in neurobiology, and does lend itself to a fairly straightforward augmentation of generative models that deal with this second order problem, or in the context of that sort of dynamic expectation maximization, the maximization step, getting your parameters of your precisions of your belief distributions right. And you can look at the sort of yeah, again, this probably won't make much sense to you, but there's a lot of work looking at sort of neuronal networks and how they can make use of cues that prompt them to attend to this as opposed to attend to that. So they know in advance where they're going to attend to. So that's the second kind, but there is a third kind. And it's a third kind which takes active inference really to the heart of active inference, and that's the planning as inference. So now, another kind of attention, which would be probably best thought of in terms of salience, is using active inference to work out what kind of attention you should deploy in order to maximize the information gain. And this is the expected free energy story, which is best developed in discrete state-space models. So I'm just forewarning you that even if you could build one of these, the game's not over. We've done that. We've done that one. That's good. You then sort of move on to this sort of much more sophisticated kind of attentional deployment known as salience, and this basically uh, asks not what in the moment, what is the best way to deploy my attention, and just to sort of nod to one of your points before about sort of allocating the resources in the right kind of way, just to keep everything roughly homogeneous, even though there's going to be fluctuations in the temperature of the processing or the precision of the processing. In the cognitive science, neuroscience literature, that's a really big thing, allocation of attention. And then you get this notion of limited attentional resources, which I think is a rather stupid idea. But what it says is that it's a system that's self-organizing in terms of the thermodynamics of information processing will look as if it's only highlighting one part of the machine at any one time and carefully controlling and orchestrating itself. So it'll look as if it's only got a limited amount of attentional resource, I mean, a limited amount of attentional resource. So if you get this right, it will look as if your machine is actually complying with a constraint, which is in terms of thermodynamic constraints, allocating resources and the constraint that there are limited resources. But you should get that for free with an active inference approach. But I just put in this here because it's just a nice discussion paper that oh no, okay, let's not do that. The sort of highlights the difference between this precision control in the moment, control as inference, but sort of pointing to the precision of your representations or your sufficient statistics or sort of what's represented by each node, and how you act by planning certain kinds of attentional moves in the future and working out what's going to be how do I deploy my attention and what will I gain in terms of information gain if I look over there or I tend to this part of the input space, or I tend to that part of the input space. So if you have a generative model of what would happen if I did that, then you can work out the information gain. And that's a different kind of attention, but it is more along the lines of salience. So I'm just saying that there are a number of opportunities here to apply active inference at increasingly, increasing levels of sophistication, which and it may well be that they all build upon each other. Before I forget, though, there is, I think, another sort of in the continuous message passing setting before we move to p-bits. The I just wanted to come to something which sort of figured quite large in the presentation. Well, no, not in the presentation, but in the postdoc discussion, which is the limitations in terms of leveraging p-bit or attention um, um, that are afforded if you're committed to synchronous updating on von Neumann architectures. When you move to mortal computation, that's a real no-no. And there's a particular reason for that. Well, there are a number of reasons. You could say, well, to comply with the principle of least action, I just have to return to the most efficient way of doing this. What's the most efficient way of doing it? Well, it's the actor model, of the 1990s. It's a sort of reactive message passing, responding to requests. So I don't do any compute until I've been asked to compute, which immediately takes you into the world of reactive message passing and asynchronous message passing. And that becomes particularly acute in the context of model computation. And there's a fundamental reason for that. And that's because as you get deep generative models apt for dealing with some content or some exchange with your world, as you get deeper into the generative model, as you get into hidden layers that are more distant from the interface or the Markov blanket, then things slow down. And in a sense, you can think of this in terms of representing the context in which the lower levels are doing compute. But the definition of a context is something that outlives in clock time the content, which means that things slow down at higher levels. So then you get into the world of deep temporal models and right back to sort of Jeff Hawkins and Dilip George in terms of hierarchical temporal models. But this is another cardinal feature of mortal computation, that the stuff which provides the empirical biases, that surprise or the inductive biases, it provides the top-down constraints that are doing the orchestration, changes more slowly than the stuff that is being contextualized at lower levels, which means that the message passing from the deeper levels is much sparse. The downwards message passing is much sorry, the rate at which I talk to my subordinates is much slower than the rate at which my subordinates talk to their subordinates, and so on all the way down, which means you've got this really interesting problem of asynchronous message passing. At what point in my computation at this level, in my computer architecture, do I now send a request to the high level for some contextual guidance? And then the higher level looks at that and says, okay, I've got this request, which has now summarized a little history, a little path of computations at the lower level. Has the context changed? And if it has, then I send the message back. But the frequency of that reciprocal message passing between level n and level n minus one is much, much slower, sometimes an order of magnitude slower than the message passing between level n minus one and n minus two. And all this now necessitates a very careful kind of reactive message passing. It goes beyond just having reactive message passing or sort of, from the actor model. It's actually now asynchronous and very structured with the separation of timescales for mortal computation.
What you're describing sounds very intuitive. I mean, it wouldn't make sense to have it the other way around, for example, would it?
No, it wouldn't. Well, yes, I'll just pick you up on that. But of course, if you've got synchronous message passing everywhere, that's what you're doing. You're completely wasting. If all the levels in your stack or your deep architecture or chatting to each other at the same rate, then that is completely inefficient, because you don't need to do it at the high levels by
Well, you can have a mesosynchronous system where the top level and the bottom level are sort of in phase,
yes,
but where obviously the top level only communicates with the bottom level every n,
yeah,
iterations or whatever. But there's a concept of being in phase,
yeah.
which is a big part of these big synchronous systems, clusters and things.
Oh, I didn't realize that. Well, I think that's spot on then. Yes. Now, if you can have a sort of phase relationship, so that there are a number of cycles at the lower level for every given cycle at the higher level, and you can do it. So, and indeed, so in some of our implementations, we actually fix n to sometimes 16 or sometimes 8. So we do sort of 8 belief updates, message up, 8 and message back down, 8 belief updates, message up and message down, and then that's repeated. So there's a little bit of a literature on that which speaks to that sort of consistent phase relationship in the context of the renormalization group and renormalizing generative models. So you can actually write this down as an architectural feature of message passing in renormalizing generative models. I haven't put that up here, but if you do a literature search on me and renormalizing generative models, you should find a paper called From Pixels to Planning. And it might be useful just to look at that, because in the introduction, there's a paragraph that gives you a number of really excellent sort of reviews of the subject that speak to this sort of phase structure. The other nice thing about this notion of phase is what I was going to say, the people that I know about who have taken this most seriously are the team led by Bert de Vries, Vries, and implemented in RxInfer. This is not particularly well. There probably some really interesting stuff that they've spent about 10 years engineering this, getting this reactive message passing apt for variational message passing on factor graphs. So this is a universal language for any sort of machine that does belief updating or computation in its most general sense. The reason I put this up is that I saw a presentation at the Applied Active Inference Institute symposium last week, where they've now got another software suite, or perhaps it's one of their partners, commercial partners, Lazy Dynamics, where they've called it a sort of CogInfer. And this CogInfer actually has this sort of phase relationship and separation temporal scales now as part of the architecture. So you can imagine a big cog deep inside your machine, and then a little cog on the periphery. And then for every rotation of your big cog, you've got lots and lots and lots of little rotations of your small cog. So it looks as though there's the levels closer to the content or the input output are belief updating more quickly or recycling more quickly than the slower machinations of the higher level. So it might be worthwhile just looking at their website and just looking for the most recent offering from this group, which is sort of, as I say, academic. I think it Delft. Anyway, you'll find out. And their spin-off, which would be Lazy Dynamics. So that speaks to the maths of and an implementation in this is in Julia of this kind of message passing. So that's them. I put this one up just to remind me, it was just to make that point about the Van Neumann bottleneck or the memory wall, and also just to remind myself to mention things like the Janinski equality, which. And I just put this up. Perhaps this is a good segue to go into the p-bit stuff. So the senior author, Bert de Vries, in this paper is, if you like, the key intellectual architect of the RxInfer reactive message passing, asynchronous message passing, specifically for active inference schemes or variational message passing schemes with deep generative models that can handle both continuous and discrete probability belief structures or probability distributions or representations. We wrote this paper just to sort of try and unpack what that perspective on computation would mean for a neurobiologist. So this paper is a useful paper because it basically what it says is that exactly the same concepts in terms of these deep generative models with action, we've got one here, can be applied to both discrete and continuous state space models. And then you can sort of work up coordinating architectures of the kind you get in the brain in terms of the requisite message passing. So the functional form of the messages is very, very similar in one sense, but very different in another sense. And that's simply because if you're committed to a variational message passing based upon continuous distributions of the exponential family, there are at least two sufficient statistics for each probability distribution. Whereas if you're committed to discrete state-space finite state machines, had Markov models, Markov decision processes, then you just need one sufficient statistic basically. So they have a different look and feel to the discrete and the continuous, but they can talk to each other. And all this paper was just about how they might talk to each other. So if you want to get a biological perspective or a biomimetic perspective on reactive message passing on a factor graph, then this might be one place to start. And I repeat, if you want to then see how it unpacks in a software context, then RxInfer would be I think the best place to go. And that brings me to sorry, this is just to for the recording. This is your Alex's paper that you so kindly mentioned in your paper. But it does remind me to make the following point. I think there's so I'm now moving over to the p-bits thing and trying to sort of give endorse or give power to your elbow for sort of pursuing the mortal computation perspective on what p-bits has to offer. And if I was thinking about this from the point of view of the brain as a sufficiency proof of the best, of the most efficient way of doing computation, it seems to me that there's a very close analogy between what the brain is doing and p-bits and the way that we simulate and model the brain using active inference and variational message passing. And basically what I'm saying is that there are two ways of describing computation on neuronal networks. One is doing exact Bayesian inference approximately via sampling, or doing approximate Bayesian inference exactly. And the mathematical link between the two is that if you take a node, for example, on a factor graph, and if it was a predictive coding scheme, you'd have a sort of auxiliary node, which would be a prediction error. Irrespective of that, if you just take a node on a neuronal network to stand in for a population, you can now ask, and you now do exact Bayesian inference in the spirit of things like sampling, MCMC, or whatever, whatever your favorite sort of Bayesian scheme is to do sampling. You can now read the sample distribution of your population of neurons as encoding a probability distribution. Very much in the same way that one could encode a quantum representation of the superposition of lots of different encodings. If you now ask yourself, well, I don't actually have the computer resources to model 1 million neurons for each node in my probabilistic graphical model. What I'm going to do, I'm going to make a mean field assumption approximation, and I'm going to work out what the density dynamics of this connected or graph of populations, neural populations, what would be the dynamics of the probability distribution if I assume that each node had an infinite number of neurons and that the neurons were idealized in the sense that they showed Gaussian random fluctuations or random effects. And then if you now work out the maths of the density dynamics that would describe the behavior of a system doing approximate exact Bayesian inference approximately through sampling, then you get approximate Bayesian inference. You get variational Bayes. So in other words, the Kalman filter is a description of an idealized neural network doing predictive coding by sampling with an infinite number of neurons to represent each thing. and then encoding the distribution over a large number of elements of any given neural population, which means that you can look at sort of simulations using things like RxInfer or simulations of active inference on a von Neumann architecture as basically emulating the limiting case of an idealized mortal computation that's doing it with lots of populations. And even more interesting from the point of view of a neurobiologist, one way of summarizing the population activity is to summarize it in terms of for a given period of time, to summarize it in terms of the spectral density, which strikes me very, very similar now to your notion of p-bits flopping around over a short period of time or at a nanosecond level. So it may well be that's exactly what the brain is doing, in the sense that, I mean, neurons don't work at the nanosecond level, but they certainly do work at the sort of tens of milliseconds level. That's where you said that, the brain is, well, you implied there is stochasticity, and of course there's the wonderful sources of stochasticity in making chips, but also the brain has some kind of stochasticity. It's not quite as marked as you might think, and it disappears when you take the population average. But at the sort of millisecond to micrometer level, there is stochasticity. There are sort of Poisson-Counting statistics in terms of interactions amongst neural populations. So there is a degree of variability in the activity over the population that can often be summarized in terms of the spectral composition, in terms of the frequencies. So it could either be sort of uniform frequencies and operating a bit like white noise, or it can be much more phasing activity. And to my mind, those different kinds of descriptions of neuronal populations at the single unit level, but in an ensemble, now lend themselves very easily to an emulation or a replication using the devices, the p-bit sort of architectures that you were describing. And now I think you can now look at variational message passing as a description of a p-bit computer that is now equipped with all the right sort of all the right transformations or message passing between the populations, between the p-bits at a slower time scale, presumably. There was if you wanted to read about the maths of that under the Laplace assumption, there's there's a really interesting connection here between precision of the kind that we were just talking about in terms of the variability um, of the variance of a probability distribution and the temperature. And it all comes from the fact that if you've got a whole bunch of p-bits that are jumping around, and you can describe them as doing threshold crossing, going over your bump in your potential energy landscape, but doing so from different starting points. And then you look at the population dynamics analytically under these idealized assumptions. You've got an infinite number of p-bits, and you've got some well-behaved stochasticity in moving around that potential energy. What falls out is a really interesting set of second-order differential equations that link the variance to the average activity of all the neurons on the p-bit. And when you write down the precision or the variance or the dependency of the population mean on the variance, you get a sigmoid function. And that's interesting because the sigmoid function is basically at the heart of all neural mass models and biometric models of population dynamics. It's also at the heart of deep learning and neural networks. Whether you write it down as a ReLU or a TANH. It is, if you can't get away from this sort of monotonic function, which is just a cumulative density function over the distribution of all the underlying elements. For you, it'll be the p-bits.
So you're making a suggestion here that sort of that of the three ways I outlined of sort of controlling p-bits, the population approach actually could work quite well, even if they're not all perfect. But I can use these techniques to apply that population approach
Yeah.
in potentially quite a simple and efficient way.
I might argue the only way. That's what I was trying to
Fair
make.
enough. Yeah, that would be a reasonable statement to make, given the complexities of what I outlined.
So, and it's because I just come back to your question about what kind of precision do I need? And once you get to this sort of sigmoid space, you start to get into the world of precisions as a precision of a softmax operator, or sort of these sort of S curve squashing functions, and the slope of the squashing function, your sigmoid activation function, if you like, is the precision of this is the inverse dispersion, it is actually the precision of your population of p-bits. So there's a beautiful mathematical link between the
Yeah.
precision as a dispersion, or inverse dispersion, and precision of the inverse temperature, and the sensitivity of at the population level in terms of the sigmoid, which means that will be the slope of your ReLU function, for example, in a neural network. So there's some really lovely mathematical links between all of these ways of conceptualizing what is precision. Is it a rate constant? Is it the amount of a measure of the thermodynamic rate, because it determines the information rate by movement on a statistical manifold? Is it a temperature? Is it a sensitivity? They're all the same thing. And they all, because they can all, when read as attention, then they all have some optimal way of being deployed, and that I think comes back to your first proposal. So that was that. That was just processing in memory, just to remind myself to make that. Some of these points. Oh, just a couple of PSs. Connor Hines is certainly. If you Yeah, the point I wanted to make here is that it may well be that the simplest application of p-bits was basically leveraging their ability just to encode probability distributions over categorical variables. So having a categorical or a distribution over categorical state spaces. And if you can deploy them, which is much simpler than this predictive coding, continuous state space stuff we've been talking about, the Laplace approximation, we're talking about something much simpler now, much closer to quantum computation. We're just saying that our generative model can be expressed in terms of the state of the world being like this, or this. And it can only be in one of these states, and therefore there's a probability distribution over it. And at its simplest, of course, if you're going right back to quantum mechanics, I'm just going to compose it's on or off, it's spin up or spin down, which means that your p-bit now completely describes a probability distribution. So it's beyond the bit, it's a probabilistic bit in the sense that you can now encode and control the probability distribution, categorical distribution over something that can be on or off, up or down or whatever. And of course, you can now compose lots of these to make arbitrarily large discrete state-space models with a accompanying Hilbert space, and of which a common example would be a Markov decision process that you can apply active inference to. So it does strike me that that would be a different application peculiar to the p-bits, just to leverage its closeness to quantum computation on the one hand, but more importantly, I think, just to recognize there's a whole class of generative models, hidden Markov models, hidden hierarchical Dirichlet processes, Markov decision processes, epsilon machines, all sorts of finite state machines that rest upon an encoding of your posteriors on in terms of some categorical distribution that I think could be very gracefully encoded as a p-bit. I think then the only job you'd have to solve is how you do your transformation. So when you look at the operators required for computation, read here as belief updating, then that basically just means a morphism from one p-bit to another p-bit. And that morphism is usually written down, under sort of classical instantiations with for example, a probability transition matrix. And you normally implement that using a sum product operator of a conventional side on a von Neumann architecture. But if you can work out some way of using p-bits or transformations of p-bits, that can be controlled, and the control is specified by the B tensor or the probability transition tensor, and you can do it in memory. I think you will have then cracked the.
Okay, so then that gives you this way to use the substrate to, manage the rest of the substrate and maybe somehow circulate that. So with the minimum of intervention, like you say, of bulky and clumsy sort of von Neumann type interventions, you want to get. I try and restate what you said. Um, I think I might actually have trouble doing that. Just repeat the 2 points again you made for me quickly. Yeah, the first set of p bits, then the second set of p bits, and the
Right.
is in between.
So one aspect, if you now read computing as effectively belief updating, what that reduces to in the context, say, I've just take a really simple, just one part of my generative model is some representation of true or false, up or down, red or blue. It's just a two-state alternative, and I need to represent the belief over this two-state alternative, acknowledging there are going to be millions of other the rest of the generative model will be compositions of these things. Let's just focus on this one, and then the most interesting stuff about this kind of generative model is the transformation per unit time at the appropriate time scale given where you are in the generative model. Of this belief into that belief. So it's this p-bit distribution into that p-bit distribution. Now, the way that that's done classically, analytically, or on a von Neumann architecture, when you write down the operators, is using a sum product operator. It's a matrix multiplication. So you take a probability 2 by 2, for example, probability transition matrix, which is what I meant by the B tensor, and then you multiply the B matrix by the p bit representation, which you will summarize as a little two vector or a vector with two elements that sum to one. So it's neither off, it's not on or off. It's just the probability distribution of being on and being off, and then you multiply that by the B tensor as you're looking at it, and that's the transformation. So if you can write in memory in the spirit of model computation, if you can somehow use your gating or changing of those potential functions or some way of moving this P distribution to this P bit distribution
without moving any p, without using the same p bit. So yeah, I got it. Yeah, understood.
Yeah. And it's all in memory. So, well, it's not even memory anymore. It's just in compute.
Right.
It's pure model computation.
Okay.
Course,
I've got it. Okay. Yeah, I understand what you're saying now.
yeah. And of course, in practice, that transformation will depend upon something else. And of course, then you have to work out how do you get the control of that transformation from something else. And that's where the message passing comes in.
Mm. Yeah, understood. Yeah.
Good.
Good.
Yeah, that's that one. Oh, yes, sorry, yeah, because it's emphasizing the importance of discrete representations and as you point out, isolating machines, and the like. I'm sure you read this. This was an early one that in fact Maxwell wrote. Just emphasize the importance of this. You sometimes use 2x, sometimes more, but I think that this getting compute to be efficient is really important for the future of sort of fun.
But there is a point there that's related to the whole mortal sort of thing, which is, brains are not programmable, but computers are expected to be. So when you say that, we have to get a computer into, to this sort of much more optimal point. Are you giving up programmability or are you not? Because programmability is useful, in real social context and socio-economic context. So what about that?
In my world, programmable means just as some way of installing priors. So you still have the opportunity to install constraints or priors into an active inference scheme, which you could say is a kind of programmability, but it would be a biomimetic kind of programmability. What it would allow you to do, which is why I think Geoffrey Hinton, who you rightly pointed out, sort of first introduced the notion of mortal computation is just to copy your weights to another machine.
No,
So
right.
you wouldn't be able to build a foundation model and then sell it to somebody else.
But if you if like you said, if you've got a set of priors you want to put, as long as I know what those priors are, I could put them in this mortal computer and that mortal computer and that mortal computer. As long as I know for each mortal computer what the local transformation or adjustment is that's required. I think what you're saying is, you would need to do that program transportation at a higher sort of more symbolic motif level than a sort of bits level.
Yes, I think that's absolutely right. A motif would be the structure. So that's what you do. You just
Which is what we have the beliefs over and you have
yeah,
the priors over.
yeah.
So if you did have a more symbolic, neuro or symbolic intelligence, then you would be better because even if that was a mortal substrate, what you're saying is if if those symbols are aligned with what we want to do as humans with those machines, we can retain programmability even in a mortal machine. That
Yeah, I mean, you raised some really interesting points there. Yeah, it wouldn't even necessarily have to be aligned with language or communicability. You just have to have some formal way of wiring up your p-bit computer parts, and the very wiring being part of the mortal computation, the very structure could now be reproduced.
you would need a schema saying I want to run this model or something on these five mortal computers, and the schema's this. Each mortal computer is capable of then configuring itself to be capable of representing that schema. Now you can move sort of constraints, if you like, or priors at a high level fungibly across those machines. But
Yeah.
you would need to have some sort of shared schema that they could all interpret. And
I see what you mean. Yes, yes. Well, schema is what I meant by structure. Yeah, absolutely. And yes, or sorry, what I was saying was you may not be able to narrate the schema. It doesn't. It may not be a large language model may not understand it, but you could
no,
certainly.
right, yeah, yeah, yeah. Well, that's what you give up to get the efficiency, right?
Yes, yes, to a certain extent. Yeah, but one could argue that there are many schema that just cannot be articulated in terms of language. Symbolic, yes, but not necessarily language.
Yeah, yeah, yeah. That's a very interesting point there at the end. I hadn't really thought of it in that way. In terms of how you could program a mortal computer, I just assumed they wouldn't ever be.
Yeah, I mean, you could certainly build one, which would be like programming it, but you might, if you want to pursue the mortal computation, it's not so much programming it, it's teaching it. And then you're leveraging its ability to adapt. A bit like fine tuning.
Mm.
The sort of foundation fine tuning, if you like, is sort of the metaphor for I think sort of inscribing your schema into your local device and then letting it learn
And
through
then
interaction.
leaving it to evolve from there.
Yeah,
Yeah,
yeah.
yeah, yeah. Well, thank you so much for making the time for me today. I'll really enjoy looking through that list of papers that you put up there. And are you going to sort of list them out, or should I just watch the recording again and sort of go find them as I run through? How do you normally do it?
No, no, normally people just run through fast forward. If you put it times two, and then just stop
Yeah, awesome.
when you find them. Yeah.
Yeah, yeah. Oh, well, thank you so much. It's been a pleasure.
Oh, well, thank you. That was really, really interesting. Oh, well, so come back and tell us when when people have made the next baby steps in this direction. That would be
Yeah, absolutely. I will do. If and when I see things happening.
brilliant.
All right. Thanks, guys.
Thank you both. That was brilliant.
Bye.
Thank you.
Take care.